Hello, everybody. Thank you so much for tuning in to this episode of Alien. We are astrobiology lessons for an interdisciplinary education network. And we are so excited today to be hosting Marc Murison. He has been an astronomer at the U.S. Naval Observatory for 30 years, before which he worked as a research astronomer at the Harvard-Smithsonian Center for Astrophysics. Marc received his Ph.D. in astronomy from the University of Wisconsin-Madison after graduating with a Bachelor of Science degree in astronomy from San Diego State University and a Bachelor of Arts degree in astronomy from Palomar Jr. College. His postdoctoral job was at the Space Telescope Science Institute, and he currently works at the U.S. Naval Observatory Flagstaff Station in Flagstaff, Arizona. But he has also worked at the National Naval Observatory in Washington, D.C. So, big fry.
Same entity, just two different places.
Yes, yes, we're so happy to have you, Marc. Thank you for being here. I am Ariel. I am a biomedical sciences and data science major at Arizona State University, and I'm here with my co-hosts.
Hi, I'm Emily. I am a senior studying astrobiology.
Hi, I'm Charlie. I'm also a senior studying astrobiology.
Hi, I'm
Taking over.
Mhm.
I'm Izzy, and I'm a junior, and I study astrophysics.
Yay.
Hi, I'm Trey, and I'm also studying astrobiology in my sophomore year.
All right.
And it seems like we've also been joined by Mark's lovely cat.
Yes.
Oh, yeah, that's Stuart.
Hi,
He's one
Stuart.
of those cats that really objects to not being the entire center of attention.
Awesome. I,
So,
for one, am happy to give attention to Stuart.
We love Stuart.
yeah. Let
Yes.
me turn off my keyboard.
Oh my gosh, such a hazard. All right, well, we can get into
Okay,
questions.
sure.
Sorry.
No worries.
First question is, could you describe your daily work and special research interests?
Okay. So I wrote a bunch of notes. So if I'm looking down, that's what I'm doing.
Cool.
Just so nobody feels like, oh, what a weird guy. I mean, you'll feel like that anyway, but it should be for valid reasons. Okay, my typical day, is that what you're asking?
Yeah.
Okay. Um, so typically I get in the morning and look at any new data from our telescopes that I care about. Um, and then set up the next night's observations. It generally means doing an analysis of all of the observations on this project to date, and then deciding, okay, based on time of night and time of year, and how frequently objects have been observed in the past, what are the best objects to observe for the next night? Uh, so I go through that, and then if I if I have submitted a job to do orbit calculations, which, as Ariel knows, takes a while sometimes, actually most times, then I'll check on the progress of that. And if any have finished, then I'll look at pretty pictures and be happy and plan the next long job and set that going. And then that's kind of the exciting part of my day. And the rest of it is real life, which, going back to the programming comment that we had earlier, I am currently working on an analysis pipeline to analyze data from a project that we're doing, and it actually, so we are observing the brightest stars in the sky photometrically. And that sounds stultifyingly boring. And part of why it seems so boring is, well, huh? Why? Haven't they been done to death? Oddly enough, no. Can anybody guess why?
Because everyone else thinks they've been done to death.
That is 50% of it, maybe 75% of it. But there's a technical reason why. Think of what we use as research astronomers. Large telescopes, right? Okay, where's the problem here?
You magnifying a big old bright thing might get a little
Yes,
hard on the equipment.
they are far, far, far too effing bright for any reasonable sized telescope to observe. And so we have a long history out here in Flagstaff of trying to figure out ways to observe very bright objects. And the reason ultimately why well, there's a science side and then there's a practical side. And the practical side is navigation. Everything about the Naval Observatory ultimately finds its roots in navigation, except for the 20% of research time that's our very own, and to hell with everybody else, we're doing what we want to do. In theory, anyway. Not ever how it works out in practice. But, so bright stars are of special interest for navigation, ultimately, but more proximately, it's every satellite has a star tracker on it. And the way satellites figure out where they are, where they're going, and how they're oriented is to take pictures of the night sky through these star trackers, and there's usually 2 of them per spacecraft. And then they match what they see with an onboard catalog that they've got, and the Naval Observatory supplies that catalog. So we are responsible for 3 things, generally speaking. Time, oddly enough, little known fact that the time that the United States uses, the time system, is from the Naval Observatory. We have a suite of 3 dozen or so atomic clocks in DC, and that averaged signal then gets uploaded to the GPS satellites twice a day. And that is what everybody uses for time. And by everybody, I mean pretty much everybody. Except the Chinese, they've got their own system, and who knows what goes on there, because they're very secretive. And the Russians, well, I don't even know if it works or not, but they've got one. And then the Europeans have been working to develop their own system, but we all tie together. So there are multiple time systems, time reference systems around the globe, and all of our times, so to speak, contribute to the international time standard, and the bulk of that is still the Naval Observatory. So time is one of ours. Another of ours is Earth orientation. We have to figure out what the Earth is doing because that's our observing platform. That's the platform that is the anchor for the reference systems that everybody uses. So we need to know what the Earth is doing because if you think about it, what distance does light travel in a vacuum in 1 nanosecond? Ariel doesn't get to participate in this. Anybody guess?
I know meters per second. Does that count?
Yeah, do the conversion however you wish.
Oh, God. Okay.
But I even have a prop, so
I
I'll
didn't know
short
I had to
circuit.
pull out a
Oh.
calculator for this.
I mean, I know it
So-
travels 1 light nanosecond.
Very good. That is an answer I would have given. But there's another answer that's a little more illustrative.
Ooh.
A foot. Oh, close to a foot. 30 centimeters for your metric. So light travels a foot. And if you need to know where you are within a few feet, you need to know what time it is to within a few nanoseconds, and you need to know the orientation of the Earth to within some fraction, tiny fraction of an arc second. For those watching YouTube and listening elsewhere, an arc second is 1/3600th of a degree, and there are 360 of those in a circle. So it's a very small angle, very small part of a very small angle. So precisions these days are at that level, so we need to know what the Earth is doing. And the third component that we have traditionally been a part of, and still are, everybody needs catalogs of various kinds of positions of objects in the sky, and that is our job. So this all ties back to bright stars in that star tracker cameras are very small aperture. I don't know what their F ratios are, but it's probably not great. So they can only look at the brightest of stars, generally down to 34th magnitude. And those are the stars we know least about. Hence this project of observing bright stars and our long-term history of trying to figure out how to observe bright stars. And long story short, what we're doing now is employing scientific CMOS-based cameras. And with those, you can take extremely short exposure times, like half a microsecond. So if you can then use this on a large telescope, well, by large I mean meter class, and normally, a meter class telescope fries at what, 7th or 8th magnitude, and you want to observe a 0th magnitude star, you need a very short exposure time. So typically the exposure times are in a handful of milliseconds. And these cameras can do that. This is also the sensor that your phone uses, and this is why you can take video with your phone, because these sensors are very fast. CMOS sensors have very fast readout times, and so you can use them as video sensors or very short exposures. So that's that project.
Very quick question, but when you say CMOS, do you mean like a marine algae? Like sea
Okay.
moss?
Oh, biologists. No, I mean, and I always forget what the acronym stands for. CMOS, metal oxide silicon is the MOS part, and the C is something. Do you all know what a CCD is? Charge coupled device?
Now
That
that you've
is,
said that, I kind of know what it stands for.
those are, that is a sensor. So a rectangular sensor, pixels by pixels. CMOS is the same, it's a sensor in a camera, and the way they operate is fundamentally different. CMOS is harder to make, but everybody wants video, and so the chip manufacturers have decided it's cost effective for them to build a ton of commercial grade devices. But kind of as a side project, there's a couple of companies that offer what we call scientific grade sensors, which means basically sensors with no flaws. And those are very expensive, and those are the ones that astronomers use. So CCDs was the first digital technology that came along, and I won't explain how either of these works. But recently, like within the past 5-ish years, a couple of companies have started offering scientific cameras specifically for science, namely biology and astronomy, because both of those disciplines have a need for low noise, high frame rate, low light levels cameras. So that's driving that. And they decided it was potentially profitable enough to give this a try, and they are fantastic. They are really nice cameras. Anyway, we've got a couple of those. We will soon be getting a larger one. So the SCMOS is scientific CMOS, and that's the scientific grade CMOS chips. So long explanation, sorry. Did
No
that answer
problem.
your question?
Yes, super informative. As a someone without much instrumental experience, it's nice to know the more specifics and also to not
Yeah.
just be hearing like SEAMOSS every time you say it.
Yeah, that's a new one on me. Okay, good to know.
Mhm.
See, we each learned something. It's always
Yeah,
good to ask questions.
a scientific exchange.
Yeah. So that is usually my day. It also a fair chunk of it gets spent in talking with colleagues about various things. They are mostly work related, not always. Um, and we are supposed to spend 20% of our time doing our own research. And generally, I mean, this is the deal that we have with the Navy. If they want real astronomers to work on astronomical projects, then they need to not bore us to tears. So whenever they need something, we jump right on it. That's our top priority project until it's done. For us here in Flagstaff, that usually means catalog. And otherwise, we have our own science projects we each do, and we generally try to dovetail those with the so-called mission projects, the ones that the Navy needs, or the DoD in general. And by the way, if any of you calls it the Department of War, I will hurt you. And that is
Wasn't planning on it.
that is the exceedingly mild opinion of every government worker.
Hmm.
Okay, no politics. So anyway, when the DoD needs something, we hop to it, and we try to sort of angle our personal science projects to piggyback off of the DoD required projects if we can. If we can't, that's fine. But if we can, that means we get to spend more time on it. So 20%, if you think about it, is 1 day a week. And so I try to do research Fridays. It often does not work out because I just have many other things to do. And this is how research falls by the wayside. So that's a cautionary warning to all of you. You have to work hard to keep to your schedule for your own science. And it's a struggle. But anyway, Research Friday. So what do I do on Fridays when I remember to do this? I have a couple of projects. One of them is very recent that Ariel worked on this past summer. Full disclosure, Ariel was an intern at the Naval Observatory Flagstaff this summer. And I tried to dissuade her from this, but she was fascinated by doing a dynamics project. That is celestial mechanics, so calculating orbits, basically, of celestial objects. And I ran across a paper that was an observational paper, and they think they have discovered a binary system with a planet in a polar orbit. So think of the binary pair, they orbit around each other. So pick a frame of reference where they're just fixed points, because then I could do it with my hands. So normal orbits are in the plane of the binary, see, either around the stars or circumbinary, and they are well, and that makes sense from an angular momentum perspective, because initially the way stars form, you have a cloud of gas that's got some very slow initial rotation because it's in a galaxy that's spinning, and the galaxy has magnetic fields, which kind of tie into the gas. And then when the gas collapses, just like a ballerina pulls in her arms, she spins faster. Same thing happens with stars when they're forming, and all of the leftover star formation stuff, gas and dust, that's left over from the formation tends to be in a disk, and then that's where the planets form. So the planets are coplanar, more or less, with each other and with the spin equator of the star. The same deal for binaries. And a polar orbit is one where the star is not in the plane of everything else, but is instead orbiting around the entire thing 90 degrees from the normal way things usually happen. And that's a weirdo. In the celestial mechanics world, that's always been a possibility, but nobody gave it any credence, really. It was more just a peculiar interest. Oh, that's cute. Huh, that's actually interesting, but it's cute. We'll never see one. Well, we've seen one, we think. So that was our motivation for this project, because the immediate question that any dynamics person will ask is this configuration stable or not? If it isn't, then how in the world are we seeing it? It has to be temporary, and if that is the case, then boy, we are extremely lucky to catch it at the right time before it goes haywire and either has a collision or ejected from the system. Or maybe it's stable. So that's what we were investigating. So there's that project, which is ongoing. And then my other project is to look at observe an ultraluminous X-ray binary. And that is a binary system that, generally speaking, is probably a black hole, maybe a neutron star. The one I'm looking at is definitely a black hole. Orbited by a companion star, which generally is an O or a B star. So a very young system, large stars, there's mass transfer, accretion disk, very, very bright. They are discovered in the X-ray, hence the name. And they are a mystery because they are too bright if the black hole is a stellar mass black hole. That is, the accretion disk is too bright. And, well, what else is there besides a stellar mass black hole? Well, the super gigantic, supermassive black holes in the centers of all galaxies. And we don't know how to make those, really, but we have theories. Astronomy has theories on how to assemble a supermassive black hole. There's a severe timing problem with that because we see them a long, long, long time ago in the age of the universe. So how do you make them that fast? Well, who knows? That's the big question there. But these ultraluminous X-ray objects are definitely binary star systems, and they are way too bright to be an ordinary mass black hole. So there are two possibilities. Both of them we don't know how to do. Either an intermediate mass black hole, i.e. hundreds to thousands to 10,000-ish solar masses. We have no idea how one could possibly make those. The other option is that it could be what's called super Eddington accretion. You astronomer majors, do you know what the Eddington limit is? Has to do with radiation pressure. Have you had that astrophysics class yet?
I'm not an astronomy major, but I'm pretty sure it has to do with it's like the max amount of possible outward energy that what was the word? Like I guess for like around a black hole, like take the accretion disk, its
Yes.
Eddington limit is like the brightest it'll shine based on like the collision of particles in the accretion disk as it gets closer to the event horizon. And the closer it get, the faster they move,
Right.
the harder the collisions, the stronger the radiation, and the more outward force it creates.
That's it
Less.
exactly. So radiation pressure balancing gravity. So if you've got stuff coming in and glowing very hot, and radiation going out, these forces oppose, and there is a limit to the amount of radiation you can have. Otherwise, you will destroy the accretion disk or divert the incoming flow of material. So that's a pretty hard limit. It's easy to calculate. And so the other possibility for these systems is so-called super Eddington accretion, which is somehow accrete at a rate that doesn't get destroyed, and yet the radiation that's being emanated from the inner part of the disk, which should destroy the disk, doesn't. And we're closer to having plausible theories for maybe how that could work. Because as in all things in science, if you look at something close enough, you will discover that things are more complicated than you thought they were. So the Eddington limit came along, and it's basically astronomical lore by now, because it's at least 100 years old, as a concept. And so we all just assume it, and that's got to be it, right? Well, back when those first papers were published by Arthur Eddington, that was the state of knowledge at the time, but we've learned a lot about radiation physics since then. So it's actually more complicated than that simple rule of thumb, maybe. So in other words, two impossibilities, or seeming impossibilities, are the only choices there are for what these things can be, these black holes, the size of them. And that's an unhappy state of affairs when you don't know how an object came to be in science. And so I'm trying to inform that question a little bit more by noticing that, well, since it is a binary system, there may be, since accretion disks are fundamentally asymmetric objects, or accretion flows anyway, and they're in orbit, so there may be a photometric signature that you could observe from this binary system. And so if you observe the light levels varying with a fixed period, within the right range of likely periods, then you can infer the mass of the black hole with a couple other assumptions, or at least a boundary for the mass of the black hole. And that would answer the question, is it stellar mass or is it intermediate mass? And so that's a really big question. They are really hard to observe because Murphy's law governs the operation of the entire universe, they are invariably exceedingly faint. So this one I'm looking at is the brightest one accessible from the northern hemisphere, and it's 21.4 or 5 magnitude, which is right at the limit of our telescopes. And so it's a long-term project of monitoring it when it's up in the sky. And if you have enough data, you can extract periods from it if there is a periodic signature to be extracted. So that's that project. And that one's hard because these systems are invariably in a complicated environment. They are new systems that is very young. The only reason we can see them in the visible range at all is because it involves an O star. So they're very bright, and they tend to be in very brand new star clusters that have just formed. So there's lots of gas and dust around and lots of closely packed cluster neighboring stars to really confuse the background. And this kind of analysis is all about background subtraction. And that is very hard when you've got a messy environment. And that's what makes this project hard, but it is fun. Anyway, that's my week.
That is so cool. Thank you for walking us through like those special research interests. I think, well, obviously I think they're cool, but but yeah, I think we could probably transition over to Izzy's question because I know Izzy, you were super excited to ask this, so take it away.
Okay, perfect. So it's like a two-part question.
Okay.
In what ways does working for the government change how you present or communicate your research? And then how do you help ensure that scientific findings are understood and used by policymakers?
Interesting pair of questions. The first one's the easier one, and that is as far as communicating or publishing, communicating in any form your research, whatever the research is, whether it's mission research or private research, it's the same. There are no restrictions. The Naval Observatory does have, and has always had, as far as I know, at least in modern times, an ed board, so that reviews our output, whatever it happens to be. I mean, it could be slides for a presentation or an abstract for a meeting, or a paper for a journal or whatever, just output. That board, which is composed of us, so we just basically review each other's papers, just to pass the laugh test, make sure we're not gonna spring forth with any real dumb errors. That's the point of that. In the DoD generally, there are editorial boards, I think, that, I mean, there are restrictions on what people can say or present to the public, because there's politics involved. But this is astronomy. There is no politics. There is no culture war going on. We are not involved in all that stuff. And astronomy is not big money, so nobody cares. So we don't have any restrictions, really, other than our colleagues laughing, potentially. So the second part, that's the hard one, because I think I would have to mark that as not applicable to me, because again, this is astronomy. Policymakers couldn't care less about astronomy, really, unless their district, if they're a congressperson, happens to be home to some ginormous project that's going to require a lot of money. Like Tucson is a hotbed because they have the Mirror Lab there, and Kitt Peak is right there. And so policymakers in Arizona do care. Okay, so I do have an answer to your question, now that I think about it. And it actually does involve us. And that is that state policymakers, state and city, they do have an interest in us, because potentially we bring in money, and we bring in, fame is the wrong word, but I'm not thinking of the right word right now, but just visibility among the public, and that's always a good thing. If it's research oriented, it's definitely always a good thing. So they like that, but ultimately, they're hoping it will lead to money for the county or the state, and that's fair. And so we do make it a point of contacting our congressional reps, to make sure that at least once a year, we try and arrange a visit so that they can come and have a tour of the observatory, and we can explain to them what it is we do, just so they know, because they need to know things. And usually it's their staff, because those are the ones that run the country. Good thing when you look at some of the politicians, but that aside, their staff, you've probably heard this before, and it is true, their staff tends to be really sharp. They are smart people, very quick. So they are just knowledge sponges, and it's delightful to talk to them, if a little bit nerve-wracking, because they can also cut off funding, if they have that power. But they're always friendly, so it's nice, with one exception, which I can talk about later. But so 99.9% of the time, they are delightful people. And so that is one avenue of approach for communicating with policymakers, and maybe not so directly influencing policy, but making sure that they don't forget about us when they come across some policy that could affect us. Because last thing they want is to mistakenly, do something bad for whatever institution is in their county or their state. So they do need to know things, and we try to let them know. And same deal with the city. The city council is a little more accessible than the state and national representatives. So it's easier to talk with them. we can just show up on a Tuesday city council meeting and let them know stuff, which we have done before, especially with regard to light pollution, which in Flagstaff is a very big deal. So in fact, we have a person who spends probably 2/3 of his time just on lighting issues and dealing with city and county and ADOT, so the Arizona Department of Transportation, which is responsible for all the street lighting across the state. And ADOT is why the Phoenix area, which is where you all are, is so very light polluted. A lot of people, bad lighting, and no lighting ordinances. Flagstaff is the opposite of that. We're getting to be a lot of people, at least from our frame of reference, and the lighting is a constant battle because places like universities and city and county lighting engineers, there's a bit of a disconnect between those people who are busy doing their engineering things for the city and the policymakers for the city or the county, because they have so much on their plate. They don't need to know the daily nitty-gritties of what the traffic engineers are doing, and the engineering staff tends to default to the cheapest stuff that's available for whatever they need to do. And that includes lighting. And the cheapest lighting right now is that ultra bright, ultra blue, prison yard looking LED lighting. And that is the very worst possible lighting you could possibly have from an astronomical and an environmental perspective, a biological perspective. It's bad for everybody.
We were like interviewing an expert on spiders, and her research goes into how artificial light at night really messes up spider development, and is just really bad for, like urban ecology in general. So it's super interesting.
Yeah, and that's a big component of it. I mean, it's important because the environment is where we live, right? That includes the night sky, and that is one of the, I guess you could call it, money makers for Flagstaff business, because come to Flagstaff, we have dark skies. That is an advertising point for the city. They like that. It brings in people, businesses like that. We like that because we have the same goals as the city does in that case, dark skies. And so that has been a happy symbiosis between us and the astronomical community and City of Flagstaff and Coconino County. And now we are roping in ADOT of all entities. It's astonishing. But our guy's really good. He talks to everybody all the time. He's constantly on the phone, constantly going to meetings, the boring kind that only traffic engineers and their bosses care about because it's just daily stuff for them. So he said, it's often just so boring in those meetings because he doesn't really care about any of it except for the lighting part, and that's usually just a small slice of any given meeting. So he has to go for the entire 3-hour meeting for his 30 seconds. So he's not a fan. But that's life. That's the way we get policy influenced for our own goals of being able to look at faint objects in the night sky. And the Naval Observatory has kind of a lever that nobody else has, and that is we have to be very careful about how we do this, but we get to trot out the national security aspect of that, of what we do, and there is a somewhat indirect connection to that. What we call mission critical projects. People really do need these things, and we really do need to be able to observe these things, so we really do need dark skies. And so that is a valid argument. And people who are much, much more diplomatic than me, they handle this. They figure out how to broach this subject without pissing anybody off, because we could, if we really wanted to, just take a club to policymakers and say, you shall do what we want because we are the DoD. Needless to say, policymakers are not real keen on that kind of behavior. So we have to be very careful. Anyway, that's long answer to what you thought was easy questions. But very good questions, because the public doesn't know about any of this stuff. So that's a really good question.
Have you seen like, what's the word? With like all the light, have you seen better observations because of that? Because of those?
We have seen, I would flip it around and say that, I mean, things are always degrading to some extent. You can't escape it. People need light at night. And whether you do it smartly or not, that is the real question. And so we try and educate the various policymaking entities about the smartest way that we currently know of to do lighting. And we do that via lighting codes. There are regulations that the city and the county have, and soon, actually kind of already, ADOT has relented, and somehow Stephen, our guy, got the ADOT lighting engineering crew up here in Flagstaff. And it was during a time a couple years ago when when Flagstaff was changing its lighting to LEDs from the low pressure sodium that we used to have, mostly. And at that time, we had various kinds of LED lights, two of which were dark skies, at least not antagonistic lighting schemes. And one is more expensive than the other, of course, and they're both more expensive than the cheapest bright white crap. So we thought it was going to be really tough sell, but the ADOT engineers came all the way up to Flagstaff and said, hey, show us. And Stephen took them around at night and showed them the various fixtures that we had around town at the time, because the city was deciding at that time. And the ADOT engineers looked at that and said, that's fine. Why don't we do that? Okay. We like the way you're thinking. Always make it sound like they thought of it, and then they'll actually follow through, which they actually have done. So the bids went out, and they are in the process of choosing the lowest, of course, bidder. They just have to, fill out the paperwork, basically giving the bidder money to do the project, and that will happen in the next month or so. And after that, they implement it. And so we will get dark skies responsible lighting, at least in the Flagstaff area. We're trying to get the county in on this as well, because Belmont is becoming a problem. And actually, from where we are up in Flagstaff, Phoenix is a problem, and it has grown significantly bigger in the last just 5 years. I've noticed the difference. It's really astonishing. The glow from Phoenix in the south, 150 miles away, is almost as bad as the glow from downtown Flagstaff, which is only 5 miles away from the
Wow,
observatory.
that's crazy.
So
Like something that
the
could is like
Flagstaff Light Dome reaches higher in the sky in the east for us, and the Phoenix Dome does not reach as high because of the distance. The light scattering in the atmosphere only goes so high, right? And so if you're further away, the top of that dome is going to be closer to your local horizon. So that's the case with Phoenix, but the brightness of that is significantly brighter than Flagstaff's. And Flagstaff's is this sort of nauseating reddish color because of the dark skies lighting. We like red because it doesn't scatter in the atmosphere nearly as much as blue light. And that is why Phoenix is so bad, because it's all blue light. So it's very intense, the Phoenix Light Dome. And it has been growing in just the last few years. It's really kind of shocking to see the change. So
I wouldn't have thought that the impact all the way to Flagstaff would be so measurable and noticeable. That's really
it
unfortunate.
is. It is. Megacity light domes are ginormous, and you can see them from a long, long ways away. So the light domes that affect us are Flagstaff, Phoenix, and can anybody guess the next one?
Is it LA?
Not a bad guess. So I only discovered this recently when I was up looking at the comet, which is my background picture. That's Comet Lemon. And I went up to Snowball, up the mountain. Just for those listening to the podcast, the mountains I'm talking about are the San Francisco Peaks, and Snowball is a ski place that sits at the bottom of it sits at 9,000 feet. And so I went up there to see what the view of the comet was, and there was a light dome on the horizon that was completely interfering with it. It kind of ruined the sky. And I got on Google Maps afterwards to find out what the hell is that? That can't be Belmont, which is the next city over to our west. And sure enough, it was Las Vegas.
Oh my God.
And then I went to another dark place south of the observatory, which is just mostly wilderness, Coconino National Forest. But there's a dry lake called Rogers Lake, so that you can actually see the horizon. And the Las Vegas Light Dome was the inhibiting factor there. So two different places here, very different places, and they both, well, the comet happened to be in that direction at that time of night, and so you're just hosed. It's Las Vegas. Amazing. So yeah, light domes matter. And we have examples of cities the size of Flagstaff that have no lighting regulations, what their light dome looks like from a distance. And from the same distance, a picture of Flagstaff, and it's night and day almost. It's astonishing what just a minimal amount of sensible lighting regulations. The main one being, well, two main ones. What is the lighting that's used on the roadways? Is it bright white, or is it, actually it's also too bright, but an amber color of some kind? So there is an amber colored LED that is relatively inexpensive to manufacture, and they have relatively long lifetimes, everybody thinks. They haven't been around long enough to really test for sure, and that's part of the Flagstaff experiment, is to give that a run in a real situation for a decade or two and see how they do. And where is I going with this? Oh, so the color of the light, and the other big one is just shield your lighting. It's not hard to do. Just put a lampshade on top of your light and direct your light at night to where you want it to go. And that actually is a glare safety hazard to have an unshielded light. If you'll notice, if you drive around Flagstaff, you'll notice at night the amber colored street lights that are LEDs, they are shielded so that if you're beyond a certain distance, you see almost nothing because the shield just blocks the light. So there's a cone that the traffic engineers have decided is necessary for safety. It's not really, but anyway, that's what they say. And that they design the fixtures so that it directs all of the light just in that cone and nowhere else. And that's a smart thing to do. There's a new housing development over on the other side of town that I was just noticing. The developer put in shielded lighting fixtures in an apartment complex, and I just about had a heart attack. It's like, whoa, somebody gets it. It's so easy to do, and it's cheaper because you can get lower wattage bulbs because you're just directing the light where you need it to go. Anyway,
Mhm.
yeah, I can harp on that all day.
Well, just a time check. We do have about 10 minutes, and I really want to make
Oh
sure we get
no!
Charlie and Trey's question. So, Charlie, go
Okay,
ahead with your question.
part two to come.
Yeah. Yeah, potentially part two.
Definitely.
Okay,
Um,
science question.
yes, science question. So I um enjoy thinking and talking about complex system science. So I wanted to see, Ariel mentioned that you do some chaos theory work, you're a dynamicist, and how have you when brought into contact with complex system science through that work? Because they seem like they would be related. And do you have any
So
opinions
like,
on this emerging field? And more of like a broad and astrobiology-esque question if you want to tackle that in a second part. But like, how is finding universal traits of a system useful for identifying life?
okay, so you're talking about so behavior at a larger scale that emerges from, like, for want of a better word, component behavior, like birds
Hmm. Hmm.
or other biological systems. They have their entity by entity or animal by animal or organism by organism interactions. And we can study those, and that's kind of a reductionist point of view, I think, at least philosophically. I mean, all of science is reductionist to them. But if you step away and look at it from on a larger scale, you can see what we are calling emergent behavior. So
Hmm.
global behavior that is not part of the individual interactions. And yet we see these beautiful things. I mean, they're invariably beautiful, like the swallow murmurations that you can see. It's like, what is going on that causes this? And I think it is still the case that we don't really know what is going on. I mean, what is it about their individual behaviors in their local sphere of knowledge, whatever that may be? I don't know how far ahead a bird looks when it's flying, but there is a distance beyond which it just doesn't care. And there is a neighbor or a bunch of neighbors, and so that is already a complicated system, and they are interacting at a detailed level in various ways, and we try to understand that. But then you step back and look at the flock of birds as a whole, and it's astonishing. It's just astonishing. And that phenomenon occurs in a lot of fields of science. And is that what you're talking about?
Yeah, yeah, because like the idea of like a complex system that you can like back up and study is present in like economics, in biology,
Hmm. Hmm.
sociology, pretty much
Yeah,
everything.
everywhere.
Yeah.
Everywhere where you have a dynamical system.
Hmm.
That is a conjecture of mine.
Ooh. And so when you're talking about a dynamical system, like what are you referring to specifically?
So it's actually pretty simple. It is just a system of things, whatever those things may be, that evolve with time, and you can identify, hopefully, a usually through physics, a set of differential equations that describe the time evolution of their behavior, whatever it happens to be. And the hard part always is the interactions of things. So in a celestial mechanics context, an astronomy context, you see it in orbits, basically. Solar system dynamics, cluster dynamics, galaxy dynamics, clusters of galaxies dynamics. I mean, it winds up being everything.
Hmm.
But the key point is that the behavior mathematically, you can model it with what we call deterministic equations of motion, usually ordinary, but often partial differential equations that are deterministic. And what that means is there's no random element to it. You can, in theory, once you know the equations and once you know the initial conditions of the system, then predict the future behavior of the system and the past behavior of the system just from the equations of motion and the initial conditions, the starting points of everything that's in the system. So that, generally speaking, is a dynamical system.
And also just a little little insert, chaos is sensitive dependence on initial conditions. So
Yes.
when we
Now, so there's a further distinction, and that is we have linear dynamical systems where the equations of motion are linear, like a spring bouncing with a weight on the end, or a pendulum. Those are linear equations. As soon as you add a joint, a second joint, to even just a simple pendulum, now it's more complicated. The equations become nonlinear, meaning that it's not a simple constant times a variable sort of behavior. That's linear. A 1 over r squared interaction strength, for example, that's gravity, that is nonlinear because of the 1 over r squared. That makes for some very exciting things that can happen. And that is where chaos comes from. And that is where we get this notion that Ariel mentioned of sensitive dependence on initial conditions. That basically is the definition of chaos, deterministic chaos. There's also what we call stochastic dynamical systems, so stochastic dynamics. And the stochastics is just a fancy word for random. There's a random process at play. Like quantum mechanics is fundamentally stochastic, we think. I mean, it just breaks everybody's brains anyway. But the easiest way to deal at the quantum level is through probability distributions. So there you go, statistics. So random statistical distributions, you can draw from them with a random number generator and do something with it. So that's a stochastic system. That's different from a deterministic system. So in deterministic mechanics, you can have nonlinear systems, and there you can be, depending on what the initial conditions are, very sensitive to the initial conditions. And it looks like random behavior. It looks completely random, but it's not. And that's, a lot of people find that a little bit confusing. What do you mean it's not random? It looks random, it talks random, it behaves random. Why isn't it random? Well, it's not. Because you can write down deterministic equations that govern the behavior of the system, or at least our model of it. And as always, the closer you look at something, the more complicated it gets. There are always more interactions happening than you thought there were at a larger scale of looking at things. And that is why science is invariably interesting, because you can look at anything, point whatever instrument you like at anything, and just keep looking closer, and you will discover new things. It's the way it's always been. I suspect it's the way it always will be. So science will never get stale.
So true. So motivating and inspiring.
Yeah, which is, so observe. That would be my advice. Always be observing, because that's where good ideas come from. Because you'll observe something and say, how does that work? Oh, I think I know how that works. Hey, that's a lot like this other thing that's my research project. I just had a brilliant idea. Somebody else would call brilliant because they didn't think of it. And because you made a random, but was it? Connection between something over here that you just were observing for the fun of it and something that has some actual scientific use. And that cross-fertilization happens all the time. And that is where most discoveries come from, is cross-fertilizing. And that is why in science it's very important to go to meetings and talk to people, because everybody always has a different angle on things. And you might make a connection that you wouldn't make otherwise for the entire rest of your life. So yeah, meetings and talking with other scientists is important.
It's a great takeaway, especially for our interdisciplinary focus.
Yes,
So
yes,
thank you. Yeah,
it
that's
is all about that. Interdisciplinary, that's a good word.
Charlie, if you need to head out, please go ahead and do so. Thank you for your question. If anybody else needs to head out, go ahead. But I was going to give Trey the opportunity to ask his question because it's really good. Or we could just put that in the part two, Trey. So it's totally up to you.
I'm good with whatever's easiest.
Okay, well, if you want to ask it now, I mean, I don't want to have you have to like be here this whole time and not ask your question. So you go ahead. But anybody can leave if they need to.
If it winds up being too long, we'll just bump it to part two.
Yes.
Exactly.
Okay.
I do have to head out. Sad to miss the question, but I'll just watch the podcast later and
Okay,
hear the
there we go.
recap. Great talking to you, Mark, and
Yeah,
have
you
a great
too.
rest of your night, everybody.
Yeah, good
Bye,
questions,
Charlie.
everybody.
Hi, Charlie. Oh, she's gone. Okay. All right.
Okay.
My question is definitely going to shift a lot more into the astrobiology side of things. And I just
Okay.
kind of want to get your opinion on something because you work with like chaos theory and like statistical and system analysis. So I wanted to ask you about, are you familiar with the mediocrity principle?
With the what?
The mediocrity principle.
Mediocrity principle?
Yeah.
Why don't you tell me?
Yeah, so it's essentially if you only have a sample of one, it's more likely to be a representation of the average than the extremes.
Yes.
Okay, so leading into my this idea of you applying the mediocrity principle with like I guess life out there in the
So
universe.
regression to the mean is what you're thinking?
Yes,
That's the same
exactly.
thing? Okay.
Okay.
Yeah, I was
So
laughing because astronomers are famous for pontificating all kinds of amazing things from one or two data points.
yeah. So um in your opinion, like, it, do you think applying the mediocrity principle, because we only have Earth as our
Hmm.
one example, like, would it be
Right.
safe to assume that like
Yeah, are we
life
average
out
or
there,
not?
yeah, would it be safe to assume that like life out in the universe is probably very similar to Earth, just because it's safer to assume that it is than it isn't. And I guess outside of life, like, has your own research led you to like, are you seeing principles or stuff that applies to the mediocrity principle as well?
Yeah, I would call it regression to the mean, if that's what
Okay.
you mean by it, because
Probably, yeah.
mediocrity has other connotations
Yeah.
that just aren't relevant, but other people won't know that. Um, so yeah, that's a sticky question. It goes back to the question that's been around since the dawn of consciousness in our species, and that is, are we special or not? And I would say my own opinion on this is, well, we don't know. It's not a question we can answer yet. And you're just gonna have to be satisfied for now with we don't know. Because, as you said, we have an example of one. We can we can theorize based on what we do know, and we do know a lot about our one example, and that could lead to a chain of reasoning whereby you can have an idea at least of how things would seem to most likely go, generally speaking. But again, it's just from a situational example of just one, so we don't know. But it seems like it should be pretty likely that life, however you define that, should exist in the universe other than here. We are actively looking for it on Mars. We will very soon be actively looking for it at Europa. And we'll see what we find. It won't be a definitive answer, of course, because it won't be other in the sense that, well, it's part of the same system that formed us, and so that doesn't count, if you think grand enough. But it does seem likely that even if our conditions that led to life were exceptional, there are a lot of stars out there. Think about it. It's hundreds of billions of stars in your average good-sized galaxy, and there are hundreds of billions of those in the universe. So billions times billions times hundreds, that very quickly becomes a very large number. And so even if it's a small probability of occurring, there's bound to be a fair number of them somewhere. Whether we'll ever see it or not, that's a different question. At least I would call it a different question.
And I think that's something that we're gonna also tackle in part two because
Yeah, it's a huge topic.
there's like a likelihood of contacts question that Mark and I were workshopping a little bit that I think we can
Yeah.
really get into. So, but that's such a good question, Trey, and I really appreciate like your explanations of the
Yeah,
meteorology.
so hold on to that thought. Because if we get a part two, we'll pick up on that. Because I did a late night sort of stream of consciousness ramble in an email to Ariel a night or two ago, and touched on a lot of these kinds of things and the chain of probabilities that would have to occur, each of which has their own likelihood number that you have to multiply into the chain. And that becomes pretty quickly a very small probability. So then you have to ask, well, okay, if we allow a timescale that's very, very long, like billions or tens of billions of years, then that small probability times that very large number means the rate of discovery of such things is all of a sudden, well, appreciable. It's significant. So you can make it happen that way. But the human species is not going to be around anywhere near that long. But you can use that. You can say, well, okay, maybe we can somewhat confidently do this chain of probabilities and incorporate a long enough time scale in order to posit a sensible rate with an error bar that's small enough that makes the rate meaningful, like so many discoveries per decade. And then the question is, well, okay, as soon as you bring in the lifespan of our species, that's a very small fraction of 10 billion years, let's say. So now you have to multiply that probability by that very small number, and you're back to very small probabilities again. So it's hard to escape that. So you just have to get lucky. That's what it amounts to, it seems. And do I have opinions on that? Maybe. I don't know. I don't think about it a lot.
Well, it's a
But
great answer. I think it goes into that idea that it's okay to have an answer of I don't know when it comes to
yes.
life
And
elsewhere. So,
if you're being honest, that will be your standard answer, always. Somebody will ask you something, you'll ask for details, and then you'll say, I don't actually know.
and
And
there's the rub of science.
yeah,
That's what we're here for.
the next step is, oh, let's go observe it and find out.
Yeah.
And that is the science cycle.
Well, thank you so much, Mark, for joining us for
Well, you're
today's
welcome.
episode. We will
Sorry
have
for
part two.
going over time.
No worries at all. No worries. It was super fascinating. So thank you. And thank you all for being here on the podcast.
Yeah, thank you all for your great questions.
We'll definitely have a part two.
Yes. Yes.
Okay, you're the organizer, so you have that power.
Yes, we do.
We have so much to get into.
Yes. For those of you who are listening, thank you so much for tuning in, and we will see you in a future episode of Alien. I hope everybody has a great night. All right. Bye, everybody. Thank you
Good
so much.
night.
Good night.
Bye.